Hello, quick video on confidence intervals and how to use them with sample means to estimate the position of the population mean. Okay, quite a lot of the time we're only working with a sample, and we want to use our sample mean to find out what our population mean is. And we're going to use these useful properties here, which we derived in a separate video, that the sample means like to be the population mean, but the standard deviation of the sample means is going to be the population standard deviation over root m. Now, the confidence interval is our range of values where we think that the population mean might be. So here we've got our sample mean, and then we're going to have our range. It's going to be plus or minus. If it's normally distributed, we can look at our z value that fits in with our probability, and then our standard deviation of our population mean over root n, because that's going to be our standard deviation of our mean, of effectively the means of the samples. If we know what our long run population mean is, so if we've been running for example, we're going to do one on heights of sixth formers. So if we've looked at the heights of sixth formers for many years, we know what standard deviation is going to be for many years and could use that. But if we don't know what that standard deviation is, then we would have to use the sample standard deviation here, sigma s, as a proxy for it. There we go. And I do mean the sample standard deviation. I mean, if we had 5 data items in our sample, 5 heights, then it is a standard deviation of those 5. And the t-distribution, and that's what the t-distribution is designed to do. Okay, so having a quick look a bit further here at confidence intervals, we're usually interested in a percentage confidence. So, for example, if we're interested in where the sample mean is going to be in 95% of occasions, and our variable is normally distributed, we can look up in our normal distribution tables and establish that we would expect it in 95% of occasions to be within 1.96 standard deviations of the mean. And in this case, we know what our mean is, our standard deviation is going to be our sigma p over root n. So if we want our confidence intervals for this, we'd be using our multiplier as being 1.96 standard deviations. Sometimes people use 99%, and if they're using that, then in our tables we know that that's 2.34 standard deviation, so we just plug that in. Okay, so let's use an example here, pupil heights. We're interested in the heights of sixth form male students, and we take a sample of 5 students and we get these heights: 170.1, 172.2 through to 168.9. And for that sample we got 2 statistics. The mean is 173.38 of that sample, and standard deviation of that sample is 3.9, which we may use later on. Okay, so we've got 2 ways of doing it. Let's have a look at the first one, which is around long run estimation. So if we've been sampling heights of sixth formers for many years, we may well know that standard deviation over many years is 6.5, and we can use that. So our confidence interval therefore is going to be our sample mean, 173.38, plus or minus the 1.96 for our 95% confidence level, and then we've got our 6.5, which is our population mean, divided by root n, our 5 here, to find our sample mean standard deviation. Those two together give us 5.7. So we've got 100. So we think our population mean is 173.38 plus or minus 5.7 centimeters. And that gives us a range 167.7 to 179.1 centimeters for our population mean. So that's quite a narrow window, really, isn't it, for a sample of 5? If we pushed it up to a sample of 10, everything would get even narrower, wouldn't it? Okay, and that's where we know what our standard deviation is. Well, if we don't know that, we're going to have to use our student t information. So here again, we're going to get our confidence interval is going to be our mean plus or minus, there's our plus or minus our t value for the confidence level we want, 95%, and our number of degrees of freedom. And our degrees of freedom are the size of our sample, in this case it's 5, take away 1 because we use that to find our mean, so that'd be 4, yeah? And as we don't know our population standard deviation, we're going to use our sample standard deviation as a proxy for it, and the t will then adjust for the uncertainty in it. So here we are. So if we want to know what our population mean is, a confidence interval of 95%, we've got our sample mean 173.38, and we've got to find our t value, which in this case is 2.776 for a 95% confidence, and 4, that's 5 minus 1 is 4 degrees of freedom. We found earlier that our sample standard deviation was 3.9, and we're going to do that square root of 5. So our plus or minus is this factor on the right hand side, which in this case is 4.85. So we've worked out that we estimate that our population mean is somewhere between 168.5 and 178.2 in 95% of the cases. So again, quite a narrow window, given that we only did a sample of 5, and of course we did 10 or 20, it would narrow considerably. Okay, so finally here's our little summary of the whole position. Okay, confidence intervals are used to find a range, and quite often we'll be either doing a 90, 95 or 99%. If we know what the long run standard deviation is, then our confidence interval for a population mean will be our sample mean plus or minus our z for a normally distributed variable times our sigma p over or root n for our sample standard deviation, sample mean standard deviation. If we don't know what our sample standard deviation is and we only got the sample to work with, we're going to take our mean value, we're going to use our t value, and we're going to multiply that by our sigma s, our sample standard deviation. I do mean that, not the sample means population now. We're just, if there's 5 items, we're finding standard deviation of the 5 items in the sample, and where v is our degrees of freedom, which will be n minus 1. So there we are. Hope that's of use. Good luck.